Okay, everybody, let's try this again. Let's do this. I'll be honest, you guys, my sparkle pen has lost its sparkle just a little bit. I have been trying to make this video all day, and I have had issues all day. So let's hope this one works. Let's see if we can put the sparkle back in my pen with this one. Let's just try this. We're going to try and write the answer key to this practice test, the fall 2015 I posted on your Blackboard. Let's see if we can write the answer key together and give you some review time and some study help time. Let's just try this. Shot number 67. Let's do this. All right, so I want to give you some ideas if I were taking the test, how I would maybe set up my cheat sheet or how I would study for this test. Remember, this test, we're starting to get just a little bit sassier. You have actually 5 different reaction types on this exam. That's a whole lot. Boy, that looks like an S, doesn't it? That is a 5. Okay, you have 5 reactions on this exam. We have radical halogenation. We have our SNs. We have our SN2. We have our SN1. We have our E1. And we have our E2. I mean, that is a whole lot of reactions for this test. And all 5 of these reactions have a completely different set of rules to them. So we can't answer anything on this test until you actually know which reaction you're dealing with. You need to know these reactions backwards and forwards. That's why you have a cheat sheet. So the first thing I would do if I were taking your test is just like we did in class. Let's start by let's look at it and let's see if we can figure out what kind of reaction is it. So let's try and identify the 4 things we mentioned in class that are always going to help us identify our reactions. We have to keep in mind our leaving group. Let's see if we can spot our leaving group. I like to start there because that's the easiest. What? There's our bromine. You can tell your leaving group right away. Remember, for your test, I'm going to keep your leaving groups to bromine and chlorine. There are other leaving groups. They are the conjugate bases to very strong acids. We're going to see in the next question that iodine is also a really good leaving group. Now, that's not on your test, but we can still answer that question. Okay, I always start with the leaving group. It's the easiest to spot. And then what comes after that is your electrophile. Your electrophile is always connected to your leaving group. So if you can start there, you can find your electrophile. Now, as we went through all of our lectures, we learned that our type of electrophile actually matters, and it helps us figure out which type of reaction we have. So I'm going to add a little information to that. That carbon and that electrophile is primary. Now that matters because some of our reactions work with primary, some of them don't. So that's a piece to the puzzle. Okay. And then I'm going to look for solvent because that's kind of the next easiest. You have a list. You have a cheat sheet that has your solvents listed. DMF is one of those solvents, and let's add a little flair for that. Remember, that is polar. Ooh, that's writing so crazy. Let's not do that. Hang on. First set of videos. All right, so it is polar aprotic. Now that's important. Only one type of reaction really uses that kind of solvent, so that's going to help us. And then number 4, this one is sometimes the trickiest. We're going to find our nucleophile or base. And I'm going to look right here at this nice ionic bond and look at that nice pair of electrons right there. That is our nucleophile. And not just is that our nucleophile, that is negative. It is a nucleophile, it's not a base. It is on your list. And it is also negative. It is not neutral. So that is going to show up on your list. You have your list of nucleophiles, and that probably looks like that on your list. Okay, so now how do you take all of this and figure out what kind of reaction it is? So each of those 5 reactions, we can start by looking at the product. All right, we didn't add a bromine or chlorine, so it's not radical halogenation. Let's cross that one off. Done. Okay. Let's look at our product. Did we form a double bond? No, so it's not an E1 or an E2. And did we end up adding our nucleophile to our electrophile? Yes. So that is telling us that this has to be one of the SNs. Oh, I'm slightly feeling my sparkle pen come back. Has to be one of the SNs. You just added a nucleophile to your electrophile. But is it an SN2 or an SN1? This is where we look at our substrates and we look at our reaction conditions and we figure out which one it is. Now I'm going to go right here and point out that our electrophile is primary. Well, if you recall from your notes, we cannot do an SN1 on a primary. So look at that. This is an SN2. Now, if I were taking your test, I would have SN2 as a nice box on your cheat sheet. I would have the rules to an SN2 because that is going to tell you what the mechanism looks like for this reaction. Our mechanisms for an SN2 are always the same and they always follow the same pattern. So once you identify that your reaction is an SN2, you can actually draw that mechanism and follow what we did in class. You know what that mechanism is. So take a second if you need to pause or screenshot or whatever this, because I'm going to erase it and actually write the answer. Okay. All right, so our SN2, if you are just studying now or if you've already written your cheat sheet, grab your cheat sheet or grab your notes. Let's find an SN2 and let's find the mechanism for an SN2. Our mechanisms always follow the same pattern for our SN2. We always start with where we have electrons, right there. We always start with our nucleophile, and we draw our arrows just like our acid-base chemistry. We draw our arrows towards our electrophile. Well, we've already identified our nucleophile and our electrophile, so the hard part is done. Let's draw the electrophile. Okay, and let's draw our nucleophile. All right, we've got those available electrons. What happened there? We've got our available electrons right there in our nucleophile, and we're going to draw towards our electrophile. Now, the 2 in an SN2 is a collision. So you have to draw your mechanism like that. There's no reinventing the wheel here. This literally is how this reaction happens. Your nucleophile smacks into your electrophile, all in one step. It is a collision. So our electrons right here, our nice available electrons, smack into our electrophile. These electrons then, this bond breaks, they leave with your bromine. So what do we make then? That is your mechanism. It's just that one step. Well, your nucleophile just formed a bond to your electrophile right there. Let's just double check our carbons. Your electrophile's got 2 carbons. There you go. And there you go. And that is our product. So out of all the mechanisms, that's probably your favorite because that's the shortest. 2 arrows, you've got your leaving group leaving, thus the name leaving group, and your nucleophile just formed a bond to your electrophile. This is awesome. All right, so that would be the answer for that first one. That's perfect. I love it. So now let's work our way down to the next question. Let's figure out if we get to draw the same mechanism or not. So let's start the whole process over. Remember, we've got our 5 reaction types. We've got radical halogenation. We've got the SNs. We've got the E's. Let's figure out which one is which. Okay, so right away, let's find our leaving group. This one is the tricky one. Iodine is your leaving group. So I'm going to spell out that my leaving group is that iodine. Now, why do we care about a leaving group? Well, it helps us find our electrophile. So let's go right to that carbon there. And what kind is it? So your electrophile is tertiary. So it's almost the opposite of the one that we just looked at. So maybe that's a signal right there that we should not be drawing the same mechanism. It is not the same as the example right above. That was only primary. This is tertiary. All right, so we've got our leaving group, we've got our electrophile. So, son of a motherless goat, look at above the arrow. There is only one thing there, and that is booze, crap. So what do we do with that? That is ethanol. So that means our life just got a little bit easier. Our solvent and our nucleophile are the same thing. So our solvent is polar protic this time. And how can that even be a nucleophile? Well, we have available electrons. They're just not negative. You've got a lone pair. You've got a nice pair right on that booze. Okay, so now what does this scream? Let's see if we can cancel some of these reactions. Let's figure out, did we add a bromine or a chlorine? No, so it's not a radical halogenation. Did we form a double bond anywhere? No, so it's not elimination. So did we substitute our nucleophile? Well, here's our nucleophile. Does this end up in our product? Yep. So it's an SN. Is it an SN1 or an SN2? Well, that's where I'm going to let this one tell me right there. This is a tertiary electrophile. So we know from class that an SN2 doesn't work on tertiary. This has to be an SN1. So right then and there, if I were grading this test for you, if you drew the same mechanism as the first question, half off immediately before I even read your question. These mechanisms are not the same. And in SN1, it is not a collision. Your starting material is going to decompose. So our mechanism is going to look different. So pause for a second, and I'm going to erase all of this, and then we're going to write that mechanism. It should be in your notes, so you should have a section on your cheat sheet or in your notes for your SN1. So let's find the SN1 mechanism, and let's draw it. So our SN1, it starts in a completely different way because it's not a collision. That's the one. So your starting material is literally going to decompose. That is the point of the 1 in the SN1. It is first order. So our leaving group leaves first. So, and it's going to leave with those electrons. That is your first step in an SN1 or an E1. Always, always lose your leaving group first. So what happens when you lose that leaving group? What do you leave behind? You leave behind a naked carbon. I mean, this is a carbocation. It is missing electrons. It's now flat. It is one black hole of missing electrons. This is phenomenally reactive. Ooh, wait a second. This is my favorite place to pause. Do you know why? Because our carbocations can rearrange. So we have to stop here and check for a rearrangement. This carbocation is tertiary. In general, we don't see those rearrange unless they rearrange for something better. So maybe on our next test that'll happen, but on this test, we tend to keep those. But our secondaries, those can rearrange. So this happens to be a tertiary. That is the sparkle pen moment. We don't need to rearrange this one. So then what happens to that carbocation? Well, you've got two things in solution. You have your iodine as your leaving group, okay? But then you've got just an absolute billion of your solvent. So your solvent has available electrons, and you have a black hole missing electrons. That is going to fill in. That is physics. You can't even stop that. Okay. So now our next step in our mechanism makes this intermediate. We just formed a bond right here. We just added booze. That hydrogen is still there. Now, I know what you're thinking. You're thinking, you know what? Forget this. I'm just going to start my mechanism and call that an O minus, and then I get to save a bunch of steps. Well, now you're talking pKa. You will not have an O minus in this solution. It's not going to be there. What's the counter to that? HI. Okay, which one wins in pKa? Ethanol or HI? Well, definitely your acid is HI, not ethanol. So you're not even going to have that. So don't think you just reinvented the wheel and you cheat and you draw that. All right, so now at this step, we're not quite done, but we're getting pretty close. We need to relieve that charge. So we can use another equivalent of booze, or sometimes in class I would use that conjugate base, even though that's not real, just to show you that HI is our byproduct. So either one of those is going to give this lone pair back to oxygen, and there's our mechanism. And now we've just formed this bond. We gave that lone pair back, and we just formed our product. And what are our byproducts? Our byproducts are booze, protonated, and I minus as our leaving group. Okay, so our mechanism is done once we get to that nice neutral product spot. And you see how our mechanism was quite a bit more intense than the SN2. They should look completely different. These were two different types of reactions. All right, so let's stop here. Let me try and post this one, and then we'll do another question. Awesome.